Welcome to the video lecture series for Texas A&M University course Math 150. Today we will look at sections 4.1, angle measure, and 4.3, right triangle trigonometry. You can find the accompanying handouts at bit.ly/RayleneMath150. Let's begin. We are going to be looking at a lot of different definitions for angles, for terminology that we need in this unit, and we'll go through these definitions one by one. First of all, when we talk about an angle measure, we can talk about angles measured in lots of different ways, arbitrarily defining angles as fractions of circles. So for instance, 1 degree is 1/360th of a circle, and another common angle measurement is a gradient, which is taking a circle, dividing it into 400 equal pieces or sectors, and then the central angle is 1 gradient or 1/400th of a circle. An angle measure called a radian, which sounds like radius, is more meaningful, and it is formed by a sector of a circle whose arc length is equal to a radius, to the radius of the circle. So if we have a circle and we have a radius here called r, if we take that same distance and travel all the way around the outside edge for the sector, so that this distance here is also r, then the central angle here of theta is equal to 1 radian. And we will make a radian in class. We can also measure angles in the degree, minutes, seconds notation, and we consider that degrees are like hours, and then minutes is a minute of a degree. A minute of an angle is 1/60th of a degree, a second is 1/60th of a minute. So let's take an example and see how we can convert degrees, minutes, and seconds. Here we have an angle given in degrees, 43.126 degrees. And we want to convert it into degrees, minutes, seconds. Well, what we see is that 43.126 degrees has a whole number part of 43 degrees and a fraction part of 0.126 degrees. So we will keep the fraction part, the whole number part, and we will convert the fraction part. So we are going to say that 43.126 degrees is equal to 43 degrees, so many minutes, and so many seconds. So let's focus on the fraction part, 0.126 degrees. And the idea for the conversion here is that there is 60 minutes to 1 hour, 60 seconds to 1 minute, and 1 hour is equivalent to 1 degree. So when we want to convert degrees or hours into minutes, we multiply by a fraction that is equivalent to 1, but the version of 1 that we want has to change units from degrees, so we have degrees in the denominator, and it has to leave us with minutes, remembering that a degree is an hour. And we ask the question, how many minutes belong to how many hours, or how many degrees? 60 minutes is equivalent to 1 hour or 1 degree. So this fraction in the green box is equal to 1. And so we can multiply by 1 and keep the value the same. So 60 times 0.126, we can work that out by hand, but let's just do it quickly with the calculator. 0.126 times 60 is 7.56. And so we have canceled off the degrees, and we are left with minutes, and we have 7.56 minutes. Now the unit that we will use for minutes is a single dash. And I'm going to erase this because it's in the way now. So far we have that 43.126 degrees is equal to 43 degrees and 7 minutes. Now what we have to do is take the 0.56 minutes and convert it into seconds. So we again multiply by a fraction that is equal to 1, getting rid of minutes and leaving us with seconds. And a symbol that we will use for seconds is a double dash. So how many seconds belong to how many minutes? Well, there are 60 seconds for every 1 minute. And so when we multiply through, the units of minutes will reduce, and we multiply 0.56 times 60, and we see 33.6 seconds. And so we can say that 43.126 degrees is 43 degrees, 7 minutes, and 33.6 seconds. We're not going to bother taking the decimal part of the seconds and converting that to another whole number part. And so here we have a conversion from degrees into degrees, minutes, seconds. And remember, 1 degree is like 1 hour. All right, let's reverse the process. Given the angle in degrees, minutes, seconds, let's convert it into degrees. So we have 300 degrees, 14 minutes, and 50 seconds. So the first thing we do is figure out how do we convert 50 seconds into minutes. So we take 50 seconds and we multiply to get rid of seconds and to keep minutes. We know that we ask the question, how many minutes belong to how many seconds? And we know that there is 1 minute for 60 seconds. The seconds unit reduces, leaving us with 50 over 6, or 5/6 of a minute, and we can convert 5/6 into a decimal. And when we do this, we see 5 divided by 6 with a decimal point will give me a decimal straight away. And let's keep maybe 3 decimal places for now. So we have 0.833 minutes. So now so far we have 300 degrees and 14.833 minutes. And we want to take the minutes part and convert it into degrees or hours. So we have 14.833 minutes, or 14 5/6 minutes, which is, as an improper fraction, 6 times 14 plus 5. So that's 60 plus 24, 84, 89 over 6 minutes, multiplied by the conversion factor of 1. So again, this fraction is equal to 1. And we need to multiply by a fraction here that is equal to 1 in order to convert from minutes into our desired units of hours or degrees. So we want to get rid of minutes and we want to keep hours or degrees. How many hours belong to how many minutes? There is 1 hour for every 60 minutes, and when we multiply through we get 89 divided by 360 degrees. And so we have this fraction we can convert to a decimal, which is approximately equal to 89 divided by 360 as a decimal is 0.24722. So let's take the first 3 digits. 0.247 degrees. And therefore we can take the minute part and convert that into degrees. So we get 300.247 degrees is our final answer, our final conversion. So really we're taking advantage of the fact that 1 hour is equal to 60 minutes, and 1 minute is equal to 60 seconds, and we are also saying that 1 hour is the same as 1 degree. So going back and forth between these conversion factors, we can get rid of the units that we don't want and keep the units that we do want until we end up with the desired angle in the desired measurements. Now if we wanted to convert from degrees into radians, we need to know what the conversion factor is from degrees to radians. Well, let's look at degrees, radians, and revolutions of a whole circle all together. We know that for 1 circle, or 1 revolution, that the total number of degrees is 360. And once we spend some more time with the make a radian activity, we will see that 1 revolution also contains 2 pi number of radians. And 2 pi is approximately 6.28 number of radians. So what we're saying is that 1 revolution is equal to 360 degrees, which is equal to 2 pi, approximately 6.28 radians, which is another way of measuring an angle that we will get more comfortable with as the unit progresses. So we want to take our answer from A, which was 300.247 degrees, approximately, and we want to convert it into radians. So we start with the angle 300.247 degrees, and we want to multiply by a fraction equal to 1 that gets rid of the units that we don't want anymore and introduces the units that we do want. And then we ask the question, how many radians belong to how many degrees? Well, 2 pi radians is equal to 360 degrees. This fraction then is equal to 1. We could take this fraction and reduce it because there's a 2 common in the top and the bottom. And so we very often use a conversion factor from degrees to radians that says 180 degrees is equal to pi number, approximately 3.14 of radians. And of course that corresponds to half a circle or half a revolution of a circle. So we can multiply by pi number of radians divided by 180 degrees. And if we do this, we will really need a decimal or a calculator. So we're going to get 300.247 divided by 180 multiplied by pi number of radians. Again, the degree symbol will reduce, and if we calculate this with a calculator, if we approximate it, we can take our previous answer plus 300, so 300 plus this number, and then we can take that quantity, multiply it by pi, and divide by 180. And we see approximately 5.2403 radians. Therefore, 300.247 degrees is approximately 5.2403 number of radians. And lastly, we want to convert this into number of revolutions. And so we can take either the degree to revolution conversion factor or the radians to revolution conversion factor. So I will take 5.2403 radians and multiply by a fraction equal to 1. That gets rid of radians and keeps revolutions. And we ask the question, how many revolutions belong to how many radians? According to this conversion factor, we know that 1 revolution is equivalent to 2 pi, which is approximately 6.28 number of radians. And so 1 revolution belongs to or is equal to 2 pi radians. And we get rid of the units of radians and we keep the units of revolutions, and we have 5.2403 divided by 2 pi, which will be approximately, taking our previous answer and dividing it by 2 pi, gives us 0.83402 revolutions. So we haven't made a full revolution. 0.843 of a revolution, which makes sense because we are more comfortable with degrees. We know that 300 degrees is not quite a full revolution because 1 full revolution is 360 degrees. All right, so let's leave the exercises page and go back to the other handout. Oh, actually we still have another exercise. Let's convert 50 RPM, which stands for revolutions per minute, or simply revolutions over minute. And we want to convert 50 RPM into degrees per hour. So the first thing we will do is see 50 rev per minute. We want to get rid of revolutions in favor of degrees. So we need a conversion factor that will get rid of revolutions and leave us with degrees. So again, we ask the question, how many degrees belong to how many revolutions? And we know that there are 360 degrees for 1 revolution. But we don't just need to get rid of the revolution units, we also need to get rid of the minutes units in favor of hours. So now we are going to multiply by a fraction which gets rid of minutes and keeps hours. When we get rid of minutes, we see that since minutes was in the denominator, to reduce, minutes must be in the top. But that means that hour must be in the bottom. But that's okay because we want hour in the bottom. So we will be reducing the minutes and leaving the hours. But we need to ask the question, how many minutes belong to how many hours? Well, there are 60 minutes in 1 hour. So we've done all the reducing, and we can multiply 50 times 360 times 60. And if we do that, we get 30 times 360, I'll just do it quickly on the calculator so I don't waste time on the video. 50 times 360 times 60 is 1.08 times 10 to the 1, 2, 3, 4, 5, 6. 1.08 times 10 to the 6, and the units are degrees per hour. We can take the same quantity and calculate or convert it into radians per second. I think I would rather work with 50 RPM than 1.08 times 10 to the 6 degrees per hour. So in part 2, I'll take my original 50 rev per minute and convert it to get rid of revolutions and keep minutes, and get radians instead, and to get rid of minutes and to keep seconds. So I ask the question, how many radians belong to how many revolutions? There are 2 pi, which is approximately 6.28 radians for 1 revolution. And how many minutes belong to how many seconds? There is 1 minute for every 60 seconds. And from here, we can start reducing. So the revolutions disappear, the minutes disappear, a 0 from the top and the bottom disappear. The 2 can reduce here, leaving me with a 3. And so I have 5 times pi times 1 all over 3. So I get 5 pi over 3 radians per second. And so all of these numbers, I'll highlight them, 50 RPM or 1.08 times 10 to the 6 degrees per hour or 5 pi by 3 radians per second. These are all equivalent quantities. And the fact that we have an angular distance, or a measure of an angle, divided by time, tells us that this quantity is going to be an angular speed, the speed at which something is rotating. And we can see different units. If we want to use the SI unit for angular speed, the SI unit is radians per second. And we will use a variable of a Greek letter called omega, which is like a curly W, to represent angular speed. It's the same notation that is used in physics. Okay, moving back to the handout with the sideways handout, we see the second set of definitions refer to the circle formulas. We are going to use the English letter S for arc length of a circle, which is, if we talk about the full arc length of a circle or of a complete circle, it is the circumference. And we measure arc length in meters, centimeters, kilometers, etc., inches. Theta is the angle measured in radians if we are using SI units, but if we don't use SI units, we could measure the angle in degrees or gradients or number of revolutions, for example. We're going to let V represent the linear speed, and the linear speed is going to be measured in meters per second or centimeters per second or hours, etc. But meters per second is the SI unit, and omega, as we just mentioned, is the angular speed, the speed at which something is rotating in radians per second. So the arc length formula is given by S equal to theta r, and the circumference is a special case where theta is equal to 2 pi. So if we were to replace the theta here with 2 pi, then we get the circumference formula. But if you only wanted to memorize or know one formula, then the general formula that you want to know is the arc length formula. Because substituting theta with 2 pi for a full revolution gives you the full arc length or circumference of a circle. The area of a sector of a circle, and again, a sector of a circle is a central angle measured from the radius to the arc length or to the circumference. This would be a sector. And so the arc length is measured along here, and then the area of the circle is the area of the shaded region. So the area of the sector has a formula of 1/2 theta r squared, and again, if we wanted the full area of a circle, we would take the full angle of theta, where theta is this central angle. If we go all the way around, theta for a full circle is equal to 2 pi radians, where radians is the SI unit. And so we substitute 2 pi for theta, just as we did for the circumference formula. And if we substitute theta with 2 pi, we get the full circle formula. But the more general formula is the one for the area of a sector, because we can use any value for theta and not talk about a whole circle, but a slice of a circle, like a slice of pizza. If we want to talk about constant speed, if we have an object that is going around and around in circles, and we want to find out what distance it is traveling in meters, then we can find the linear distance divided by time to be the linear speed. So v is equal to the linear distance of s for arc length divided by the time it takes to travel. The angular speed is the same formula, but in terms of the angle distance or angular distance of theta. So we have theta, it's hard to read here, divided by time to give us the angular speed, which we said is measured in radians per second. So the linear and the angular speed will be the linear distance equal to the angular distance times the radius divided by time. So we can convert the arc length formula into the distance formula by dividing by time. And when we divide by time, we see that s divided by t equals theta r divided by t, and s over t, we can separate the theta r over t to just be theta divided by t, and s divided by t is v, theta divided by t is omega, and times r. So we have a very similar relationship between the linear and the angular distances and the linear and the angular speeds. So we'll talk more about this in the exercises. Let's take a look. For circumference, we want to show that the arc length formula s equals theta r, where s is the length of a circular arc measured in meters or centimeters, etc. And theta is the angular distance measured in radians, and r is the radius measured in the same units as s. Then we get the formula for the arc length, or the circumference of a circle. Well, if s is equal to theta r for any arc length, then theta equals to 2 pi radians corresponds with the arc length of a whole circle. But of course, the arc length of a whole circle is called the circumference of the circle. And so we get the circumference by substituting 2 pi in for theta. So when we put 2 pi here and we multiply by r, then this distance is the arc length, but it's the special arc length of the whole circle, which is called the circumference. And so this is just a reminder that this is the special formula, the special case, and the original formula for arc length is the general case. So it's best to remember the general case over the special case. All right, the next thing to take a look at is to work with the linear and the angular distance formulas. Let's consider a ladybug who is sitting at rest on a turntable, and the turntable is going to be rotating with a constant speed. And the ladybug is sitting here. Well, technically she should be sitting at the edge, because there's no indication of where she's sitting, so we will assume that she's right on the edge. And she's at a distance of 14 centimeters away from the center, because that's the radius of the turntable. And so the turntable is going to be moving, and we want to determine the angular, measured in radians, or the linear, measured in circumference, distance that the bug travels. So if the bug travels, makes one complete revolution, then what does one complete revolution measure? That's a measure of the angular distance, so we know that theta is equal to 1 revolution. Since we have the angle, we want to find the linear distance s, and we know that the formula relating s and theta is s equals theta r. Now the problem with substituting theta equal to 1 is that this 1 revolution is not using the SI units. So the first thing we have to do before using this formula is convert to SI units. And so we know that theta, I should put the formula underneath here. equal to 1 revolution must be multiplied by 1, getting rid of revolutions and keeping radians. We ask the question, how many radians belongs to how many revolutions? There are 2 pi, or approximately 6.28 radians for every 1 revolution, and therefore theta is equal to 2 pi radians. Now, and only now, can we use the formula to solve for to solve for s. So we replace theta with 2 pi radians, and we multiply by the radius, which is 14 centimeters. The units of radians are what we call dimensionless, which means that when we multiply by a dimensionless unit, it's like it's not there. It's just a placeholder unit, because this radian, as we will understand better from the make a radian activity, this radian is a ratio of the arc length over the radius, and as a ratio it does not carry any units. So what that means is that radians multiplied by centimeters is equal to centimeters. So we have 2 pi times 14 is 28 pi, and the units is centimeters. So approximately 28 times 3.14 number of centimeters. Okay, let's try part B. In part B, we are given the angle that the ladybug travels through is now 4.5 revolutions. So 4.5 revolutions must first be converted into radians for use in the formula, because radians is the SI unit. Which means before we use any of the formulas, we have to have the SI unit for theta. So we ask the question, if we want to get rid of revolutions and keep radians, how many radians belongs to how many revolutions? Again, it's 2 pi radians to 1 revolution. And 4.5 is 9 over 2. Multiplied by 2 pi gives us 9 pi, and the units we keep are radians. Now we can use the formula for arc length, which says S, arc length, in centimeters or meters, the linear distance, is equal to theta times r. Theta is 9 pi radians. The radius is still 14 centimeters. And we have 90 plus 36 is 126 centimeters. Again, radians times centimeters is centimeters. In part C, the table rotates through 200 degrees. This is the angle, but again, the angle is not given in the SI units. So the first thing we have to do is convert from degrees to radians. Then we can use the formula. I'll leave part C to be done as an exercise. Part D says that the bug travels 57 centimeters. Because the units are the linear distance units, we are given S. And from S, we want to work backwards to calculate, in this case, the angular distance, or the value for theta. So the angular distance is theta, and the linear distance is S. And the relationship between the two quantities is S is equal to theta r. But the important thing to remember is that theta has to be measured in the SI unit of radians. So I'll leave you to try part D as well, and we'll talk about it when we meet. Example 4 is the relationship between linear and angular speed. So just as the linear distance is equal to the angular distance times the radius, this is for distance, if we have constant speed, then we divide by time, and s divided by t equals theta r divided by t, or theta over t times r. And this quantity is called v for the linear speed, and this quantity is called omega for the angular speed. So the linear speed is equal to now let me put in brackets that the linear speed is v equals the angular speed of omega, which has to be measured in radians per second for the SI units, times the radius, times the radius. And the units of v and r are the same. Okay, so let's take a look. The ladybug is resting on a turntable now of radius 10 centimeters, and it is rotating at 40 revolutions per minute. This is not the SI units of rad per second, and so we must convert, at least the revolutions has to be converted to the radians. We don't always have to convert minutes into seconds, but we are asked, first of all, for her angular speed in rad per second. So the radius of 10 centimeters is not important to us. What we do have to do is a conversion from 40 RPM into rad per second. So in part A, we start off with 40. I like to write revolutions per minute as a fraction, and then I have a conversion process to do. I have to get rid of revolutions, and I have to get rid of minutes. And I want to keep or get radians, and I want to get seconds. So then I ask the question, how many radians belong to how many revolutions? In this case, we have 2 pi radians for 1 revolution. And how many minutes belong to how many seconds? 1 minute belongs to 60 seconds. So we can start reducing. And we can reduce the 2 here with the 6 to give me 3. And so I have 4 times pi radians times 1 over 1 times 3 seconds. And so we get 4 pi by 3 rad per second. So that's part A. Part B asks, what is her linear speed in SI units? So what we really have in part A, I should really label this and not just do a calculation. The angular speed is 40 RPM, revolutions per minute, which is also an angular speed of 4 pi by 3 rad per second. In part B, we want the angular speed, which is we want the linear speed, v, which is the angular speed times the radius. There are lots of different versions of the angular speed that we could use, but we want the one that involves the SI units to be substituted into the formula. So we are not going to use 40 as the number for omega. We are going to use 4 pi by 3 because we need to use the correct units. And so we have 4 pi by 3 rad per second multiplied by the radius of 10 centimeters. So we get 40 pi over 3 rad times centimeters over seconds, and radians times centimeters is just radians because this is a dimensionless unit, and we get 40 pi over 3 centimeters per second. In part C, we are told that a wad of gum is stuck to the turntable 5 centimeters from the central axis, from the turning point, from the center. Compare the angular and linear speeds of the gum compared with those of the ladybug. Well, in part C, let's just draw a little picture. We have our turntable. We have that the ladybug is resting on the turntable of radius 10. Again, it wasn't clear in the problem, and a test question would be clearer, but we will assume that she's at the edge, which gives her a radius or distance from the center of 10 centimeters. And we have a wad of gum at a radius of 5 centimeters. So this distance is 5, and this distance is 10. If we want to talk about the angular speed, we know that the ladybug is going at 40 revolutions per minute. But the wad of gum in the same time frame is going to travel the same angle. And so the ladybug and the gum have the same angular speed. But because the wad of gum is on a smaller circular path, because it's at a smaller radius than the ladybug, it is going to travel fewer centimeters and therefore have a different linear speed from the ladybug. So we can talk about the angular speed of the gum, and notice that it's the same as the angular speed of the ladybug, which is 4 pi by 3 rad per second. However, the linear speed of the gum is going to be different from the linear speed of the ladybug because the gum is going to travel a smaller circumference or a smaller arc length in the same time frame as the ladybug. So if we take a look at the ladybug's distance in a certain time frame, this might be at time 0. This is time 0, and this is some later amount of time. In that time frame, they have traveled the same angle, but the arc length of the ladybug is much bigger than the arc length of the gum. And so if we want to find the arc length of the gum, or the linear distance of the gum, we can say that v for the gum is equal to arc length of the gum multiplied by radius of the gum. And it's the fact that the gum is at a radius of 5 compared to the ladybug being at twice the radius, which says that the linear distances and therefore linear speeds of the ladybug and the gum will be different. So we know that the angular speed of the gum is 4 pi by 3 rad per second, multiplied by the radius of the gum, which is only 5 centimeters, which gives us 20 pi by 3. Radians times centimeters is centimeters over seconds. So we see that the linear speed of the gum is only half that of the linear speed of the ladybug. So the ladybug's linear speed is 40 pi by 3, and that of the gum is only 20 pi by 3, because the gum is half the radius of the ladybug. The last part of this question is, does the ladybug experience any acceleration? Well, let's just remember what acceleration is by definition. Acceleration is the rate of change of velocity with respect to time. And velocity is composed of, it's a vector quantity, and so velocity is composed of speed or magnitude, how fast is something going, and also where is it going, direction. Well, if the velocity is not changing, then there is no acceleration. But because we have velocity as two different components, we have to take a look at, is the speed changing and is the direction changing in each case. So is the speed changing? Is the ladybug's speed changing? Well, we have two kinds of speed. When we're talking about acceleration here, we'll look at the linear speed. Is the ladybug's linear speed changing? No, she's going at a constant linear speed. She's taking the same distance in the same amount of time over and over again. What about her direction? Is the ladybug's direction changing? In this case, the answer is yes. She is constantly changing direction. Because she is constantly changing direction, she will have acceleration that is responsible for changing direction. And we define in physics that the acceleration responsible for changing direction, or responsible for changes in direction, is called centripetal acceleration. We won't work out the formula for centripetal acceleration, but we will make connections to physics later on. Okay, let's move on to the next piece. Example 5, let's derive the area of a sector formula with modeling. So let's model, like we've been doing in exponential change, to prove that the formula for the area of a sector of a circle is given by a equals 1/2 r squared theta, or a equals 1/2 theta r squared. So when we talk about the area of a sector of a circle, we notice that if we take the radius and we draw a central angle, so we have some arc length along the circumference, and we have a radius here and a radius here, we have an angle theta. And we have a certain amount of arc length. Well, let's make a table of values. The radius is going to be constant in this circle, so theta is changing, and the area of the sector will change. The theta is the independent or input variable, and arc length is like y. So this is like x and y. And we know that if the central angle is 0, meaning that we're on a straight line, then there is no sector, and the area of that no sector would be 0. So when the angle is 0, the area is 0. But then if we double the angle, so we take another angle of size theta, what happens to the area of the sector? So if we have an angle here called theta, and let's call the area A, then if we have an angle of 2 theta, what happens to the area? Well, the shaded area is twice the previous area in red. And if we triple the angle, then the resulting area is triple the previous or original area. What kinds of functions have this behavior? Well, when we think about it, this is a linear behavior. So we're expecting that the area to be some kind of linear function of theta. So if we have a linear function, we might say that linear function is y equals mx plus b, but y represents area and x represents theta. So we need to solve for the two parameters of m and b. We also happen to know some other information, but let's just think about this. From a point of view of modeling, we have two parameters, which means we need two ordered pairs. Well, we have one ordered pair of 0, 0, if we were to look at the area and the angle theta graph. We know that 0, 0 is a point on the graph. These are not really points on the graph because neither theta nor a are known. But we do happen to know for a full circle the area is pi r squared, and at that instance the angle is 2 pi. So we have 2 points. When the angle is 2 pi, the area is pi r squared, and that's a second point on the graph, and we have a linear relationship because of the doubling the angle producing double the area relationship. So we can take these 2 points and solve for m and b. The fact is the y-intercept is 0 because the line goes through the origin, and now we just need to solve for this scale factor, or this m. So we can take our second point, which is 2 pi comma pi r squared. We can substitute pi r squared in for a, and we can substitute 2 pi in for theta. So when we do this, we can reduce both sides by pi, and we see that m is equal to 1/2 times r squared. So that's the slope of this line. And we see that area as a function of theta must be 1/2 r squared times theta, or 1/2 theta r squared. And that's the formula that we were desired to prove. So we're done. In the next example, we want to use that formula to determine and calculate the area and the arc length of a sector. So we want to find the arc length and the area of a sector that is 1/8 of a circle with radius 7 centimeters. So we have a 7 centimeter circle, radius circle, and we want to go 1/8 of the way around. And so our sector is this size piece. We want to find the arc length S, and we want to find the area A of the slice. So the arc length formula says S equals theta r, and in this case theta is equal to 1/8 of a circle. That 1/8 of a circle is really in revolutions, and so what we need to do is convert from revolutions into radians, because radians is the SI unit. So we want to ask the question, how many radians belong to how many revolutions? 2 pi radians belongs to 1 revolution, and when we simplify this, we get that theta is equal to pi over 4. I think my picture is wrong. My picture should be here. Yeah, that's 1/8 of a revolution. There's my S, and there's my area. And we have pi over 4 radians. So now we can use this value and substitute it into the formula. So S, the linear distance measured in centimeters, is going to be pi over 4 radians multiplied by 7 centimeters, which gives me 7 pi over 4 radians times centimeters, which is just centimeters. And in part B, we want to know the area of that slice. There are lots of ways to do it. We could recognize that this is 1/8 of the whole circle. The whole circle has an area given by pi r squared, and so we could just take that area and divide it by 8. To use the formula, we could say area is equal to 1/2 times theta r squared. And in order to use theta in this formula, we have to use the SI units of radians. If we are going to use this formula, then we can substitute in. So we get 1/2 times pi by 4 radians times 7 centimeters squared, which gives us 49 pi over 8 radians times centimeters squared, which is just centimeters squared. Okay, last example using linear and angular motion and the formulas relating s, theta, v, and omega. The belt on an automobile air conditioner connects two metal wheels, one with radius of 5 centimeters and the other with radius of 15 centimeters. Let's draw a picture. So I'm going to have a blue smaller radius wheel of 5 centimeters and a red larger wheel of radius 15 centimeters. And I have a belt that connects these two. Really see where I'm going. So the belt goes around and connects the two wheels. Okay, the larger wheel rotates at 120 RPM. We do need to be careful of the units and recognize what this quantity is. RPM is rev per minute, so this is an angular speed. And so we know that for the red belt, let me call it omega for the larger wheel, is equal to 120 rev per minute. We really should get in the habit of converting non-SI units, non-radian angles, into radians straight away before we do anything else. Sometimes the question will ask that, but not usually. So we want to know what is the larger wheel's angular speed in radians per second. So for part A, we take the large wheel's angular speed and we multiply by 1 enough times to get the units to what we desire. So we want to get rid of revolutions and keep radians, and we want to get rid of minutes and keep seconds. How many radians belong to how many revolutions? There are 2 pi radians for 1 revolution. And how many minutes belong to how many seconds? There is 1 minute for 60 seconds. So we can reduce our units. We can reduce some of the numbers. And we end up with 2 times 2 pi rad over 1 second, which gives me 4 pi rad per second. Part B then says, what is this larger wheel's linear speed? Well, the formula relating linear and angular speed is V equals omega r. I think I'll do it all in red for the larger wheel. So the speed of the linear speed of the larger wheel is equal to the angular speed of the larger wheel multiplied by the radius of the larger wheel. We have the angular speed in SI units and we have the radius of the larger wheel. So we get 4 pi rad per second multiplied by 15 centimeters, and we are going to get 60 pi rad centimeters per second, but radians times centimeters is centimeters. Okay, in part C, what is the smaller wheel's linear speed? Well, unlike the ladybug and the gum, which was on the same circle and therefore had the same angular speed, these two wheels are going to have the same linear speed. That is the whole purpose of the belt. The belt, if we were to slice it, would be a straight line or linear distance measured in centimeters. And so because the belt is connected to the two wheels, the purpose of the belt is to force the two wheels to have the same linear speed. Again, reminding ourselves of the case with the ladybug and the gum, they were on the same wheel with different radius, and being on the same wheel meant that the gum and the ladybug had the same angular speed. So in part C, we want the smaller wheel's linear speed, so we want omega for the small wheel. It's not going to be the same, we want the linear speed. So we want V for the small wheel. And V for the small wheel is equal to V for the large wheel because the belt forces the two wheels to have the same linear speed. And I'm just going to call it V. And then in part D, we want to know the angular speed of the belt, of the smaller belt. So we have the angular speed is a question mark. We can start off with the formula that the linear speed equals the angular speed times the radius. And we can solve for angular speed as being the linear speed divided by the radius of the small wheel. The linear speed of the small belt is 60 pi centimeters per second, divided by the radius of the small belt, which is 5 centimeters. And here centimeters here and here reduce. 5 goes into 60 12 times. So the angular speed of the small belt is going to equal 12 pi per second. But centimeters divided by centimeters is dimensionless, and so we can put a placeholder unit for the angle of radians in place. So contrast this question with the ladybug and the gum question, because in this case, the two wheels connected by the linear belt going around in a distance measured in centimeters means that the two belts have the same linear speed, whereas in the case of the ladybug and the gum, being on the same wheel, those two objects had the same angular speed. Okay, there are lots more definitions that we need to go through, and we'll try to go through the definitions quickly. If you need to, pause, read the definitions until you are very clear. You need to have a good working vocabulary and sense of the terminology for the rest of the unit. So please pay particular attention to these definitions. Different terms for angles. If we want to measure an angle, it begins at an initial arm and is measured towards the terminal arm. So this is like a theta or an angle initial, and this is an angle final. And theta is the distance between angle final minus angle initial. It's like a delta theta, really. An acute angle is between 0 and 90 degrees. A right angle is equal to 90 degrees. Obtuse is between 90 and 180. A straight angle equals 180 degrees. And a reflex angle is more than 180 but less than 360. Complementary angles are two angles that sum to 90 degrees, and supplementary angles are two angles that sum to 180. We will always measure a positive angle in the counterclockwise direction, and we will measure negative angles in the clockwise direction. So if I wanted to go negative 90 degrees, for example, I might start at the 0 standard position and go 90 degrees clockwise. So an angle down here is negative 90 degrees. Quadrantal angles are the angles like 0, 90, 180, 270, and 360 degrees that lie on the axes. So we will talk about standard position of an angle. We will start at the positive side of the x-axis and measure 0 degrees. Then 90 degrees in a positive counterclockwise direction lands on the positive side of the y-axis, 180 degrees here, 270 degrees here, 360 degrees here, 450 degrees here, etc., going all the way around and around. The non-quadrantal angles are all the other angles that lie in the quadrants. And so if I have an angle measured from the x-axis, the positive side of the x-axis over here, I don't want it in green, then from my initial arm to my terminal arm, I have an angle theta that does not lie on an axis, and so it lies in a quadrant. These angles are called non-quadrantal angles if they lie in a quadrant. Okay, some more definitions. The standard position, as we mentioned, is when the initial arm is at 0 degrees on the positive side of the right of the x-axis, and we measure in a counterclockwise direction, a positive direction. Compass position, however, is when we take the positive side of the y-axis to be north, and then south, east, and west as the normal compass position of an angle. We will be dealing with converting all compass position angles into standard position for working with trigonometry. We want standard position angles. Standard position or standard form looks like the first picture, but we have to make sure that the vertex of the angle lies at the origin, not off the origin, and we want to make sure that the initial arm is not any angle, but it's specifically along the positive side of the x-axis at an angle of 0 degrees. Principal and coterminal angles. In these definitions, we will talk about any angle that lies in the first rotation of the terminal arm. That sounds confusing. All we're saying is if we start with a terminal arm on the positive side of the x-axis at 0 degrees, where we begin standard position, and we measure in a positive direction, which is counterclockwise, then within the first revolution, any angle that lies at any terminal or ending arm within the first revolution is called a standard position angle. It's called a principal angle. Principal just means one or in the first. So in the first revolution of an arm, this arm revolves around. Any angle in that first revolution is the principal angle. Now I could get to the angle here, 120 degrees, by wrapping around more than one revolution. And as soon as I wrap around more than one revolution, it is not a principal angle, but it is a coterminal angle to that principal angle. The prefix co means to share. So any two angles that share the same terminal arm are coterminal. They're not the same angle. They may differ by 360 or 720 or 1080 degrees, for example. They will differ by 1 or 2 or 3 or more revolutions. So this is another example of wrapping around more than once, and we have a positive coterminal angle to 120 of 480 degrees. If we wrap around another revolution, we have another coterminal angle to 120 and 480 of 840 degrees. Or if we go in the opposite direction, in the negative direction or clockwise direction, then we have negative 240 degrees. The principal angle will always lie between 0 and 360 degrees, not equal to 360, but equal to 0. We don't include 360 degrees because 360 is coterminal to 0 degrees. And we can only have one principal angle. So we include 0 as the principal, but not 360 for this side of the x-axis. So a negative angle cannot be the principal angle because it is not between 0 and 360. The next type of speed quiz that we will be having for trigonometry will be to convert from degrees to radians. I'm going to do a couple of these and have you fill in the table on your own. We know the conversion factor that one revolution is equal to 2 pi radians, which is equal to 360 degrees. But if we're only interested in converting from radians and degrees between the two, we can divide this part of the proportion and say that pi number of radians is equal to 180 degrees if we divide this by 2. Of course, that's equal to half a revolution if we take the whole statement and divide by 2. So pi radians is equal to 180 degrees. So 180 degrees is equal to pi radians. We tend to get a little lazy and not write the radians because it's assumed to be there if no other unit is. If we were to write 180, then the assumption is that that angle is 180 radians, not degrees. So do be careful in your use of the units. Okay, so let's fill in some more of this. If pi radians is 180 degrees, then half of that is 90 degrees or pi by 2. And if we take 90 degrees and divide by 3, we get 30 degrees. So, or we could take 180 and divide by 6 to get to 30 degrees. So pi divided by 6 radians is 30 degrees. Similarly, 180 divided by 3 gets me to 60 degrees. So pi radians divided by 3 is pi by 3 radians, which is equivalent to 60 degrees. I could take 60 degrees and multiply by 4, for example, to get 240. So I could take pi by 3 radians and multiply by 4, so that 4 pi by 3 radians is equivalent to 240. You should get in the habit then of being able to place these angles on the circle. And I'll just do a couple. We have 0 degrees here, 90 degrees at the top of the y-axis, 180 degrees, which is half a revolution, 270 degrees, which is 3/4 of a revolution, and back around at the coterminal angle, 360 degrees, lies along the positive side of the x-axis. Halfway between 0 and 90 degrees then is 45 degrees. A third of the way between those two, of 90 and 0, is 30 degrees and 60 degrees. Over here we have 30 degrees away from 180 degrees is 150, and all of the angles that are here will be plotted in the green, purple, turquoise, or black lines. So once you've finished completing this, it would be practical if you wrote both the degree and the radian angle beside each of the terminal arms so that you can get very comfortable with how big these angles are. So I'll leave this for you to be finished as an exercise. Okay, here's another picture if you want to use that, the drawing to practice with doing it again. All right, another type of angle definition that we need is the reference or related acute angle. You will see again, if we go back, that all of these lines that are in green happen to have something in common. From the nearest x-axis, they are all the same distance or the same angle away. They are all 30 degrees away from the x-axis. And depending on whether we are measuring in a clockwise or a counterclockwise, we either add or subtract 30 degrees. So for example, starting from 0, going in a counterclockwise direction, we add 30 degrees and get 30. Starting from 180 degrees, we subtract 30 degrees, and because we're going in a clockwise direction, which is negative, so 180 minus 30 is 150 degrees. 180 plus 30 degrees gives me 210 degrees. And since 210 is 30 degrees multiplied by 7, 210 degrees is 7 pi by 6. So 7 times pi by 6 gives us 7 pi by 6, which is this angle measured from the beginning all the way to the end in radians. And lastly, we could say 0 minus 30 degrees is negative 30 degrees, but that's not the principal angle, because principal angles, I'm using theta for the angle, lies between 0 degrees inclusive up to but not including 360 degrees. And a negative number does not lie in this interval. And so we would instead get the angle for this terminal arm by going all the way around like this, which means we are going up to 360 degrees and then back 30 degrees. So 360 minus 30 degrees gives us an angle of 330 degrees, which we can figure out in radian form. Okay, so then the reference angle is any angle in standard position that has an angle measured from the nearest x-axis to that angle. So if we start from an angle of 30 degrees, we measure between 30 degrees and 0, and we see that the reference angle is 30. An angle in quadrant 2 of 150 degrees is 30 degrees away from the nearest x-axis. An angle of 210 degrees is 30 degrees away from the nearest x-axis, and an angle of 330 degrees is 30 degrees away from the nearest x-axis. So we always measure reference or related acute angles from the nearest x-axis to the terminal arm. So these are 4 principal angles in different quadrants: 30 degrees, 150 degrees, 210 degrees, and 330 degrees. And we notice that they all have a reference or related acute angle of 30 degrees. Going back then to this picture, all of these angles in green, 30, 150 degrees, 210 degrees, and 330 degrees, I've drawn them all in the same color as an indication that they all have the same reference angle of 30 degrees. Similarly for all the purple angles and for all of the turquoise angles. We never measure reference angles from the vertical axis or the y-axis. The reason for that is just to keep it consistent. If some of us measured reference angles from the y-axis, then this would be a measurement of 30 degrees, but instead we say that the turquoise angle has a reference angle of 60 degrees. So we just have to keep it consistent, and therefore we will never measure from the vertical axis to get the reference angle. Angles that lie on an axis, like 0 degrees, 90 degrees, 180 degrees, 270 degrees, etc., they do not have a reference angle because they are either on the x-axis, which means they are 0 degrees away, or they are on the y-axis, which means they are 90 degrees away. And the reference angle has to be an acute angle, which means between 0 and 90 degrees and not equal to 0 degrees or 90 degrees. So only non-quadrantal angles that lie in the quadrants have reference angles. Okay, so let's just practice this. I'll have you fill most of this in on your own. We want to classify the angles by the reference angles. In the first type, we are going to have all the angles lying on the axis. It's not very clear from the picture what the angles are, so I'm just going to highlight the angles that we wanted to refer to. And these angles are the quadrantal angles at 0 degrees, 90 degrees, 180 degrees, 270 degrees. So the type of angle is quadrantal. And because these angles do not lie in a quadrant, they have no reference angle. The next angles that we are talking about are not the axis angles, but they are the, maybe I'll use the green highlighter. They are the green highlighted angles. And again, they are all the angles in a quadrant, so they are the non-quadrantal angles. And in this particular case, we can see that the measurement from the terminal arm to the nearest x-axis is a space of 30 degrees. And so we should be familiar already with these angles being 30 degrees, 150 degrees in quadrant 2. This is quadrant 1, this is quadrant 2, this is quadrant 3, this is quadrant 4. The quadrant 3 angle with a reference of 30 degrees is 180 plus 30 degrees is 210. And 360 degrees minus 30 degrees is 330 degrees. So in each of these, I would like you to put the radian measure beside so that we're getting very fast for our speed quiz, converting between all of the angles in degree and radian form. So you should be doing it for all of the specified angles. In this case, the reference angle is 30 degrees or pi by 6 radians. So complete that for the other two pictures. We have, let's see, I'll highlight the angles here. We've got purple, consistent with the other diagram, and we have turquoise angles here. Okay, always measure the reference angles to the nearest x-axis. So all of these angles in purple have the same reference angle. All of these angles in turquoise have the same reference angle. Put both the angle in degrees and radians for each of the 4 angles in the picture and complete this yourself. Okay, almost through. The anatomy of a right triangle. If we take a look at a right triangle, then we definitely have a right angle in one of the corners, and opposite that angle is the hypotenuse, the largest side of the right triangle. Then if we specify one of the remaining 2 acute angles as theta, then one side is adjacent to theta, and the other side is the opposite side to theta. If I were to label a different angle alpha, then the altitude of the triangle would be the adjacent, but this time it's adjacent to alpha, not to theta, whereas the base of the triangle would be the opposite side to alpha. So it's important when we're labeling the side of a triangle as the opposite or the adjacent that we know which angle we are referring to call it the opposite or adjacent side. So when we want to talk about ratios of triangles, we do have to have one of the 2 acute angles in mind when we're talking about opposite versus adjacent. Because we've got 3 sides, we can come up with 6 different ratios or fractions, taking 2 sides at a time. The 6 ratios are opposite over hypotenuse, or its reciprocal, adjacent over hypotenuse, or its reciprocal, and the opposite side over the adjacent side, or its reciprocal. Of course, these are with respect to one of the 2 acute angles. And so we're going to make some definitions of trig functions, just like we had exponential functions, logarithmic functions, power functions, rational functions. We're going to come up with trig functions, which are based on these 6 ratios. We are going to refer to the given angle of theta, and in terms of the angle theta, or with respect to the angle theta, we are going to say that the sine of the angle theta is the opposite side divided by the hypotenuse. And its reciprocal is taking hypotenuse over opposite. We will call it the cosecant function. And we have the long words written over here. The ratio of adjacent over hypotenuse for a specified angle will be called the cosine function of that angle. Reciprocating that fraction gives us hypotenuse over adjacent, and it is called the secant, S-E-C-A-N-T function of the angle. And then taking the other pair of sides, opposite over adjacent, gives us the tangent of the referenced angle. The reciprocal of that is adjacent over opposite side, which is the cotangent of the angle. So these are some definitions of trig functions based on the 3 sides of the triangle taken as a ratio or a fraction, 2 sides at a time. So we are going to take a look at proving a fundamental trig identity. It is true that the tangent ratio of theta is equal to the sine theta over the cosine of theta. Well, remembering that the sine of theta has been defined to be the opposite side of theta over the hypotenuse side of the triangle. Hypotenuse is always opposite the right angle. Then we can say from the right-hand side, RS is sine theta over cosine theta. But the sine of the angle is the opposite over hypotenuse, and the cosine of the angle is the adjacent over hypotenuse. So instead of dividing 2 fractions, we take the first fraction and multiply by the reciprocal of the second. The hypotenuse reduces, leaving us with the ratio of opposite over adjacent. But by definition, the opposite side over the adjacent side for an angle theta is called the tangent of theta, and we've converted the right side of this statement into the left side. And so because the left side is equal to the right side, we're done, QED. Well, we can try the proof over here for cotangent theta, and I will leave that to you as an exercise. Please have it completed in your video check completion. 2 more things to go. 2 special triangles that we want to know and have memorized so that we can do some quick calculations of trig functions, much in the same way that we memorized the powers of 2 so that we could quickly calculate that the log base 2 of 1024 is 10. This is the same thing in the trigonometry unit as what we did by memorizing 2 to the 1, 2 to the 2, etc. So over here, the way to get started is to draw 2 right triangles. One of the right triangles is isosceles, which means that 2 sides are the same. The other triangle is scalene, so all 3 sides are different. And we're going to start off with the first 4 counting numbers, 1, 2, 3, and 4, and we are going to take their square roots. And we're going to simplify them if we can. And we can simplify the square root of 1 is 1, and the square root of 4 is 2. These are the 4 numbers that we are going to fill in the 2 triangles. Well, we know that the hypotenuse is the largest side of a right triangle. The hypotenuse cannot be exceeded. And the largest of the 4 side length possibilities is 2. We're going to take both of these triangles to have the same hypotenuse. So we've used up 2, and we have 3 more sides to choose. Let's now work out what the isosceles triangle leg length is going to be by calling that A. We now know a relationship between these 3 sides, or among these 3 sides of the triangle, and that relationship is the Pythagorean theorem. So we're going to solve for A by saying that a squared plus a squared is equal to 2 squared. Therefore, 2a squared is equal to 4. A squared is equal to 2. So a is plus or minus square root of 2, but a is a distance, so a has to be the positive square root of 2 only, because the negative root is extraneous. We cannot have a negative distance. And so we now know that the square root of 2 is used up, and the side here is called square root of 2. Well, given that in mind, we should go back and put in the angles, which I've omitted here. The 45-degree angle fits into the isosceles triangle for both of these. And we have 2 other angles of 30 degrees or 60 degrees. the smaller angle is opposite the smaller side, and the larger angle is opposite the larger side. That's the reason why the hypotenuse is opposite the right angle, because it is the largest angle in a triangle. So the shorter side seems to be my altitude, so opposite that is the smaller angle. The base is the larger of the two legs, so the 60-degree angle goes here. So opposite the smaller angle goes the smaller side, and we've used up one. And opposite the middle angle goes the middle length side, and the square root of 3 goes here. Of course, we could scale these triangles and make them any proportion that we want. If we keep the triangles similar, we could use a consistent horizontal and vertical scale factor of k, which means that all of the side lengths would be multiplied by a. So this would be 1a, or sorry, I said k for the scale factor. So this could be, going around in circles, this could be, still doing that, this could be 1k, this could be 2k, and this could be the square root of 3 times k. So if k is equal to 2, this length could be 4, this length could be 2, and this length could be 2 times the square root of 3. We could do the same thing for the isosceles triangle and scale it consistently. If we scale it in all directions equally, then the angles are preserved. This is what it means to have a similar triangle. And when we do this, this could be 2k, square root of 2k, and square root of 2k. Okay, last thing that we want to have some speed recall with, or to memorize, are these Pythagorean triples. Pythagorean triples are sets of 3 numbers that satisfy Pythagorean theorem. So if we have a 3, 4, 5 right triangle, what that means is 3 squared plus 4 squared is equal to 5 squared. Now the angles here are not 30 degrees and 60 degrees, which is what a lot of students assume. These side lengths are not related to the 2 special triangles because they are not in the same proportions of 1, square root 3, and 2. But these are nice, neat whole numbers that do satisfy a squared plus b squared equal to c squared for a right triangle. This is because 9 plus 16 does equal 25. But of course, if 3, 4, 5 is a triangle, then 3k, 4k, and 5k is also a right triangle, which means that 3k squared plus 5k squared, plus 4k squared is equal to 5k squared. And so we could take that same triangle, preserve whatever these angles are, let me call them alpha and beta, keeping the triangles similar, and having different lengths. So this could be 3, 4, 5, this could be 6, 8, 10, or it could be 30, 40, 50, or it could be 3 over 2, 4 over 2, 5 over 2, and Pythagorean theorem would still hold, which means that no matter how we scale the triangle, if we preserve the angles, then we have similar triangles and the sides are in proportion. So one Pythagorean triple that would be practical to memorize is 3, 4, 5. Another Pythagorean triple is 5, 12, 13. A third Pythagorean triple is 7, 24, 25. And the final Pythagorean triple to memorize is 8, 15, 17. Knowing these would make it a lot easier to solve certain lengths of triangles because we just know the proportions of 8, 15, 17, or the side lengths of 8, 15, 17 are commonly found. But we have to make sure that if we have 15 here and 8 here, that we don't assume that 17 is the missing side. Of course, 17 has to be the biggest side because it is the biggest number for the hypotenuse. So if we have 8 and 15 as 2 sides of the right triangle, if 15 is the hypotenuse, you would still need to use Pythagorean theorem to solve for the missing. So a squared plus 8 squared is equal to 15 squared. So a squared is equal to 225 minus 64, and we can proceed from there. So it's also a good thing we've memorized these squares so that we can work out Pythagorean theorem quickly. This concludes section 4.1 and 4.3 on angle measures and introduction to trigonometry. Please ensure that you've completed the handout and created a list of clarifying questions. That's all for now.